So let's see some examples of how to use these powers of 2 to solve some real interesting problems. The first one is how many bits would be needed to store the number 750. When I'm looking at this problem, I'm going to try to think through all the powers of 2, and I'm going to try to find the 2 powers of 2 that bracket the number 750. So I'll put 750 here in the middle, and then I think about what numbers would be on either side of 750. Well, I think 750 is probably going to be in between 512, which is a power of 2, and 1024, which is also a power of 2. And so I know that if I need a number 750 to be represented, it will need more bits than the number of bits that can be used to store 512, but it will need no more bits than the number that would be used to store 1024. So 512, this is 2 to the 9th power, and 1024, this is 2 to the 10th power. So I know that I'm going to need more than 9 bits, but no more than 10 bits. And so therefore, I'm going to say that this number can be represented in 10 bits. And that's my answer for representing 750. What's the largest number that could be stored with 9 bits? Well, we kind of gave that one away in part A, but if we think about 2 to the 9th power, and you can actually use your calculator to do this calculation, or you might have it memorized, it is equal to 512. And you might say, well, that's ridiculous, I'm not going to have all those numbers memorized, but you only really need to memorize a few numbers. If I remember 2 to the 8th, which is an extremely important number to electrical and computer engineers, I know that that's equal to 256. Well, I know that 2 to the 9th is just 2 times 2 to the 8th, or 2 times 256, which is 512. So I don't need to use my calculator to do that. I just remember, say, 2 to the 4th, 2 to the 6th, 2 to the 8th, and 2 to the 10th. And everything after that is easy. I know that I'm going to need to represent one of these 512 values is going to need to be used for 0. So I can't really technically, 0 needs to be counted, but it isn't one of the positive values that I'm going to be counting. So I'm going to say that one of these is going to be used to represent 0. And so therefore, I don't have 2 to the nth number of largest numbers. I'm going to have 2 to the nth minus 1. So I'm going to have 512 minus 1 equals 511. And so 511 is going to be the largest number. So I could say that the numbers 0 through 511 are going to be represented with 9 bits, and so therefore 511 would be the largest of that range. Now, approximately, what is the value of 202 to the 25th power? And this word approximately here, when I'm talking about powers of 2, there's really only one approximately that I need to worry about, and that is that, that 2 to the 10th is equal to 1024, which is approximately 1000. Now it's off by, a little bit there. It's off by about 2%, but for the sort of ballpark calculations that we're going to be working with, it's a very reasonable approximation. So I know that 2 to the 10th is approximately 1000, and I know that therefore 2 to the 20th is 2 to the 10th times 2 to the 10th, which is 1,000, which is approximately equal to 1,000 times 1,000, which is equal to 1 million. So 2 to the 20th power is approximately equal to 1 million. I know that I have 2 to the 20th, but I have an extra 5 here. So I need to know what is 2 to the 5th power. Well, 2 to the 5th power is in between 2 to the 4th and 2 to the 6th. 2 to the 4th is 16. If I go up another power of 2, that's equal to 32. Or I could say 2 to the 6th is 64, come down a power of 2 down to 32. So I know that 2 to the 25th is equal to 2 to the 20th times 2 to the 5th, which is approximately equal to 1 million times 32, which is 32 million. Now the actual number is a little bit higher than 32 million, but it's still a very good approximation for us to think about, roughly how much would be able to be represented in that. And then what power of 2 is approximately 4 billion? This is kind of working it the other way. So 4 billion here, when I think about 2 to the 10th is approximately 1,000. 2 to the 20th is approximately 1 million. And 2 to the 30th is approximately 1 billion. And so if I need 4 billion, Well, that's going to be an extra 2 to the second power is 4. So 2 to the 30th times 2 to the second is 1 billion times 4, or 4 billion. And then all I need to do is take those two numbers and say that this will be 30 plus 2 is 32 bits. And 32 bits is a very important number of bits that we'll work with quite a bit, and so therefore the value 4 billion will be something that we're going to see quite a bit as well.